we have in other graph no momentum yet, we know that the gradient descent with respect to Wg at this point. What we take a scalar product of these gradients by multiplying it by alpha, so when we create a scalar, and this guy, it is actually our introduced approximation of the Hessian. Because we take again the vector derivatives, we multiply it again with the vector of the derivatives by the gradient, and also to make it more stable, we accumulate this over the steps. Similar to what we have done in the numerical methods. So we just add to j minus 1 this additional vector gradients. So when we take the square root, we obtain the exact thing we want to do, and epsilon is something we need to make it more stable because this thing can be not very good. Yes?
Could you repeat this one more time? How this connected with coefficient conformation matrix? This result.
Okay, the idea here, okay, we have this scalar product of partial derivatives, yes? And we know that this guy is close to the vector of, to the Hessian, to the diagonal representation of Hessian. So in the Newton methods, we would have the following rule for the update of the parameters. Yes, this is a classical methods when we have the inverse Hessian. Here we replace the inverse Hessian with the matrix of second derivatives and also use the diagonal approximation. So each jt would be this square of the partial derivatives. Also we take square root to normalize everything and add epsilon to make everything more stable. So basically we replace h with r diagonal, and in r diagonal we replace with this matrix of the squares of g x e in this notation g G as component squared. And we exactly place this thing back in J to obtain approximation of a second order basis. Okay.
But in the Newton method we have inverse H, and in the previous slide we said that we can approximate like just Hessian, not inverse one.
Not what?
In the Newton method, we have inverse Hessian.
Yes.
And you said that the product of first derivatives is the approximation of just Hessian, not
Yes.
inverse one.
No. But we need to put inverse Hessian here. So we need to look at the inverse of this thing here, like 1 divided by 2, to make the inverse of the vessel. Maybe not very clear, so basically, we say that we need to put h in the power inverse. We say instead, let's look h diagonal inverse. This is the matrix that consists, like this, the diagonal of h I is power minus 1, yes? So now, if we have this inverse diagonal elements of the Hessian, the formula would result like alpha divided by the vector of diagonal parts of the Hessian. Yes, this vector consists of h I. And the last step here is to replace h I with something we can estimate. And we say this HI this guy, according to the Fisher theorem, is close to this guy here. Okay, I is component squared. The only thing that is not very well explained in this talk is why do we need to take the square root. And actually I don't know how to answer this. But anyway, it's pretty close to what we expect. Okay?
Okay.
So, we have this other graph, and actually we are pretty close to finally defining the anomalies. In this way, okay, you can skip this, this. And finally, the atom used, I suppose by most of you in your routine optimization programs. We just combine this idea of approximation integration and the idea of taking the momentum approach instead of the usual approach, the gradients. So basically, we say our WG plus 1 would be WG minus the learning rate multiplied by the part that relates to the approximation with second order optimization and the part related to the momentum for our gradients. So basically, the momentum for our gradients is defined seen before. Yes, we take the gradients and we have a linear sum of previous gradients accumulated over previous steps. This coefficient is not in one. For G of t, we also apply the similar idea with momentum, but now we accumulate momentum for the products of these derivatives. And we have a separate coefficient, mu and pi corresponding to 1 minus 1. And in this way, we obtain this formula of n. That actually combined ideas from previous methods, but it was so successful, still used in 2025 actually. Okay, 10 years has passed since the introduction of n. And now we can also understand each part of it. Also, you can think about this term about second order optimization and so on, but you can just say it's kind of normalization of the word. Just take the square of the gradient and take the square root of it and display. Yes?
So, if this term is normalization of the gradient, basically we are just taking more controlled steps each time. If the gradient is closed, we don't make these steps.
Yes.
Okay.
Okay, we accumulate it, we also have this thing. Also, the momentum is good not only because we are talking about this increase in the convergence speed from theory, but also it is a good idea because we are typically working in batches. We never calculate the gradients in respect to all the training data. We take a small batch of data, take the gradient because it's a small batch, and update our values. But if we apply this momentum approach, then we are better in kind of basically calculating the gradient with respect to bigger batch sizes. So we can say this approximation to increased batch size also can be pretty useful if you are talking about that we want to increase the amount of information at each step. Also some things about the job, the performance of the thing, and some historical example of what people were doing in 2020. Okay, another question. Who of you know what is MIST? MIST, yes.
Yeah. The data set with
Handwriting digits, yes.
handwriting digits.
And who don't know? Okay. So, MIST is about recognition of handwriting digits, something like image like this, and we need to predict that it is 9, and for this, it is something, for example, it's 1. And so we need to do this, and it was one of the first data sets that became standard at that times, and people typically did not have so much compute. Actually, I suppose the size of this image is 28 by 28. It's pretty small compared to the modern ImageNet. On one channel is black and white pictures and so on. And the sample size is something like 60,000, so pretty small if you're looking at it in 2025, but back then it was a standard tool to assess how good an approach is. And they looked at the performance of this approach for multi-layer neural network. Also, you can see that it is even not a convolutional neural network. It's just simply fully connected layers stacked one by one. It's 2 or 3 layers. And then we doing experiments in this setting, and then compared different options. Some of them were selected. For example, here is undergrad, accelerated gradients by Nesterov, we talked about repeating, and RMS probe, and other delta, I suppose we talked about, or no, it doesn't matter much, it was the thought at that time, and we can see that RM is much more successful in decreasing actually the loss function with respect to the number of iterations of the data set. It was more successful than approaches that had fewer components. The same thing goes on for other methods, like it was CPAR-10. Another data set we mentioned times is 10 possible places, it's all images again, but now they at least have some colors in them. And we can even see that it works for convolutional neural networks. And again, we can see that now it is used also. Okay, to finalize this part of the lecture and maybe the overall lecture. We were talking about how to optimize parameters of a neural network. There is a very specific optimization problem because of 2 things. The first thing is that it requires a lot of time to calculate the gradients because typical structure of the loss function for it is a sum of big number of terms where m is the sample size. Y is the true variable, X is our input image, and W is our parameters we want to optimize. Another problem with this thing is that it doesn't belong to any reasonable class optimization problems. We can say that it's convex, we can say it's linear, quadratic, whatever. And also, if we look at this functional, typically it is quite a regular thing. So it has many local minima and it's not easy to optimize and not easy to obtain some numerical properties. So nothing can be better than some empirical methods. And also, we need to compute the gradients. The backpropagation was introduced, I suppose, 40, maybe 50 years ago. The efficient way to calculate the gradients of E with respect to W over multiple layers. Pretty easy to grasp, and I suppose it's not harder than applying a product rule for calculating the gradients. I suppose all of you know the product rule from your calculus course. And so we have this complex optimization problem, and we need to solve it at least with some accuracy. Find some good global outcome. And the first thing we need to pay attention to is now we are in the world of stochastic optimization. We never compute these terms for all object material sample. Each time we select some subsample of objects from the training sample and compute the gradients with respect to it. The second thing is that due to the number of parameters for W, we need to think carefully about introduction with second order methods. And the most common option here is to use the called add-on that unites the idea of momentum, accumulated gradients through multiple iterations optimization, and this normalization by the square root of the square of the gradients. And also, if this also we can consider some options to select the momentum coefficient, the rate ratio, and this is something you should also master in practice with some initial insights given in this lecture. And also, if you can try this accelerated gradient, sometimes it can perform better, but I suppose for smaller problems. For large scale problems, adding is the best typically you can get. So also, sometimes some square term work is used. There is a slide on it. To the slide show you can go back to it and find out the work of this. And I suppose that's all I wanted to talk. Today, unfortunately, we were not very successful at covering convolutional neural networks, so see about it next time. Yes?
Excuse me, can you please repeat why don't we calculate the loss on the folders?
The reason is very simple. Suppose this M is, I don't know, imaginary size 10 millions. It means the calculation of the loss is linear in the number of terms. And we just can't afford calculation of the loss over the full data set. Also, another limitation here is the memory requirement. Actually, to calculate the loss, it's more convenient because of how GPU graphic processing units works to fit all the weight of selected objects into the memory. And if we can do this, we are in a pretty bad state because we need to replace these things due to the need to replace one batch of objects with another batch of objects during the calculation of the gradients. And because of these two reasons, we can't opt for big batches. Actually, in practice, you need to select the batch size. I see. You need to select as the biggest possible batch that fit into your memory. But given the constraints, we can do this, so we somehow should approximate the total gradient. Yes, for you.
I have a question. So, as I understand, we have a function from weights to R, for example, and this function depends on our neural